Hello and welcome to the next video. In the last video we had studied that if I have a current carrying wire where uh, it produces a magnetic field around near its region, and if the direction of the current in the straight wire I is in this direction going up, then we studied in last video that if we applied our right hand thumb rules, our fingers will curl towards the direction of the magnetic field, which will be which I have summarized here. The magnet direction of magnetic field will be anti-clockwise like this, and so to the left of the wire, uh, it is it will here the magnetic field will come out. So the notation of magnetic field coming out will be like this. The magnetic field is coming out, going around, and to the right of the wire it will go inside the screen of the inside the computer screen, plane of the computer screen. So here the direction will be like this. Suppose we keep another wire, say to the right side of this, and it also carries a current I. So that means that I have placed another wire near the original wire. This wire is also carrying a current I. That means I have placed another wire in a region which already has a magnetic field due to this wire. So this wire has a magnetic field. So again, because of this wire, there is a magnetic field all around in this region which is going inside this, and we know from our last to last video that if a current carrying wire is placed in any magnetic field, it experiences a force of equal to, say, a small force of dF. So any unit length, any length, small length dl will face a force of I. Suppose this current is I1 and this current is I2. So if I place a magnetic wire, an electrical wire which is carrying current I2 in a magnetic field B, suppose this magnetic field is B due to this wire, so this is the magnetic field B created because of this wire, and the small force is given by I dl cross P. And if I find the notation of if I find the direction of df, dl is the vector dl is along this direction of the current, and B in this particular case is going in. So if I apply the rules of cross product, my right hand thumb rule which we were discussing in the first video of magnetic field, we will know that it experiences a force in this direction. That means that this wire attracts another wire, because it experiences a force towards it, it is attracting this wire towards it. So that concludes that if I have two parallel wires which are carrying current in the same direction, then they will start attracting each other because of the magnetic field they produce. Now let us find out, from the last video we knew that if I have a very long wire or infinite wire, then the magnetic field created by this wire, the very long wire, will be given by B will be equal to, magnitude of B will be equal to mu naught I by 2 pi d. Okay, so I can find the small force dF just by substituting the value of B from here to here. Now here it is I dl cross B. Now dl is along I2, and so the magnitude of df will be equal to I dl B. We know cross B means dl into B into sine of theta, and because the magnetic field is going into the plane of paper and I2 is in the plane of this paper or computer screen, that means B and dl is making a 90-degree with each other, and so sine theta sine 90 will be 1. So this will become as I dl B. And now if I just substitute the value of B, I will get from here to now here, df will be equal to I dl into mu naught I. Now here this is the magnetic field due to this wire, so here I must write I1, and here the force is on the second wire which is carrying current I2. So here I must write I2 to distinguish it. So df will be equal to I2 dl, and instead of B I will write mu naught I1 divided by 2 pi d, where d will be the separation distance between these two wires. So if I just rearrange df by dl will be equal to mu naught I1 I2 by 2 pi d. So this gives us a very important and useful formula. It says that whenever I place two current carrying wires near to each other separated by a distance d, they exert a force on each other. The force may be either attractive or repulsive. It is attractive when both the wires are carrying the current in same direction. It will be repulsive when one wire is carrying a current in opposite direction, and the force per unit length which they exert upon each other will be given by mu naught I1 I2 by 2 pi d. So this is one very useful formula. Next, another very useful topic to discuss is, now we have discussed that if I have a straight conducting wire, it carries it creates a magnetic field around itself like this. What if I have a circular wire? Now we will discuss a circular wire. So there are two cases. So circular wire will also have a magnetic field around itself. Suppose the wire is carrying a current in an anti-clockwise direction, okay, and so I want to find the magnetic field at its center. Case 1 is magnetic field at the center, magnetic field at center, okay. So as usual we will use the Biot-Savart law. The Biot-Savart law says that the magnitude, we will first find the magnitude and then we will move on to find the direction. How to find the direction? So first let us discuss the magnitude. Magnitude is given by mu naught by 4 pi I dl sin theta by r squared, okay. So here if I draw a tangent, suppose I want to find this point. So here dl vectors, let me say take a small element here, okay. If I take a small element here, then the radius, if I want to find the magnetic field at the center because of this small element, so the radius or the r vector will be just simple joining of the line of the two things of the dl element and the center. And if I say draw a tangent to this, okay, that we know that tangents are always perpendicular to the radius. So that means the r vector makes an angle of 90 degree with the element vector in case of a small element which can be thought of the part of a circle also, as well as the tangent also, because it is very small. So since this makes an angle of 90 degree to this r vector, so this is r, this is dl, let me say it as a, okay, a is the radius. So a or r I am denoting as a. R vector makes an angle of 90 degrees, so sine of 90 degrees is 1. So this will just become mu naught by 4 pi I dl by, instead of r I will just say a squared. Okay, I am denoting the radius of the circle as a squared. So this is the small magnetic field due to this small element dl. Now if I want to find the total magnetic field, it is very similar to what we did to find the electric field in our electrostatics chapter. I will just integrate from 0 to b, and I will again integrate this. I will not put limit because it is a very simple integral now. What I will do is I will just take out the constants out of the integration sign, mu naught. So it is just an integral of over the surface of the sphere, or line integral. So mu naught by 4 pi I by a squared integration of dl. So integration of dl is, if I integrate the dl over the whole circle, I will just get the circumference of the circle. So integration of dl is nothing but the circumference, which is equal to mu naught, let me write down the full expression, I by a squared, and integration of dl is the circumference of the circle, which is 4 pi a. So pi will get cancelled, this will become 2 and this will just become a. So the final answer is mu naught I by 2a. So the magnetic field at the center of a wire which is carrying a current of a circular wire which is carrying a current of I and has a radius a, the magnitude of magnetic field is given by B is equal to mu naught I by 2a. Now what about the direction? Okay, so the direction of the center here, the direction of the loop of the magnetic field will be along the axis. Along the axis, why? Because I know that the magnetic field should be, because it is a cross product, B is a cross product of dl vector into r vector. Okay, so it should be perpendicular to both the dl vector, for dl vector as well as the r vector. So the only possible way in which it can be perpendicular to both dl vector and r vector is that the magnetic field will either come out of the plane of paper or go into the plane of paper. So it is like this. Okay, from perspective view, I have this, suppose this is the dl direction, and we know that radius, or sorry, this is the, okay, this is the dl direction and this is the radius direction. This was the dl direction. Sorry, in this case it is just the opposite, because the current is flowing like this, that is from right to left along the dl. So it will be like this dl, and the radius is from line joining from here to the center. So the radius vector is like this, or r vector is like this. The only possible direction which is perpendicular to both this and this is the direction which is coming out of the plane of your screen. So the axis, suppose this is the x axis, this is the y axis, z axis is the only remaining axis which will be perpendicular to the both x as well as y. So the direction of magnetic field will be along the z axis or out of the screen or towards the screen. So the z axis has two possible direction. One is the positive direction which is out of the screen, or the negative direction which is inside the screen. So let us find out how to find the direction of the magnetic field along the z, whether it is coming out or going in. So again, because I am very bad at making figures of hands and all, I was trying to help something in from the Google images, and I have found one. So look at this. I have a circular carrying current wire. Okay, circular carrying current wire. So I will again use the right hand thumb rule, but now my right hand thumb rule, because now my eye is curling or my eye is going round and round, I will use my fingers in such a way that it will follow the path of eye. So I will curl my finger along the eye. So if eye is in anti-clockwise direction, I will curl my finger along anti-clockwise direction. If eye is clockwise, then I will try to curl my finger along the clockwise direction. So in this case, eye is along anti-clockwise direction. So when I curl my finger towards anti-clockwise direction, my thumb will come out. Okay, it will come out of the screen of the plane of your screen. So this is the way we can find the direction of current. So if it is anti-clockwise, it will come out of your screen of paper by using the right hand thumb rule. If it is clockwise, by again if I invert my hand, it will and make my fingers curl along clockwise direction, then my thumb will point towards inside if the current is flowing in a clockwise direction. So magnetic field will come out if I is in anti-clockwise, it will go inside the screen if it is in clockwise direction. So with this we have discussed one simple case of the magnetic field due to a current carrying loop at its center. Let us now discuss a more general case. More general case is more general case of a circular current carrying wire. So the more general case will be, I have a circular loop of wire. It is like it is an isometric view. I have, and I want to find the magnitude of magnetic field at a point in a, not at its center, but a general point in its axis. So let me take this point in its axis, and which is say at a distance of d from the center of the circular loop, and say that the radius of this circle is again a for a general case, and I want to find what is the magnetic field at this. So again I will take a very small element dl along this. Suppose again here my current is in anti-clockwise direction, so my dl vector is so suppose this radius is going inside my screen, and so this is, say, this is along this is my x axis, this is my x, this is my y, and the perpendicular direction is z, and this loop is in yz plane. This circular loop is in an isometric view which is in yz plane, and the axis is the x axis. Okay, so hope you get the 3D picture here. And So because of this small wire dl, okay, my r vector will be the line joining the dl with this, okay. Direction will be always toward this point. My dl vector because it is in yz plane, okay, my dl vector will be along the z axis. If you can imagine the dl which I have taken here. But anyway, if I just use my right hand, because B is direction of B is given by the product of dl cross r, so it is both perpendicular to dl as well as r. So my magnetic field will look like something will be in this direction, perpendicular to r. Okay, so this is the small magnetic field dB because of this. Similarly, if I take another wire at an opposite end, okay, and again if I draw a r here, and because of this my net dB will be small dB because of this element will be like this. So we see that for every element there is an diametrically opposite element whose, because both are of same dl and both are at same distance r, dB will be, magnitude of dB will be same because of the both these small elements. So the y component will get cancelled, okay, the y component will get cancelled because they will be equal and opposite to each other. The only component which will remain is the component along this direction, which is the x direction. And if I take, say, this as theta, so the dB cos theta will be the actual contributing factor which will not get cancelled out. So if we add this dB, this component of magnetic field for all the small elements, I will get the total magnetic field at this point because of this wire. So just let us substitute. We know from Biot-Savart law what will be the small dB. If this is r, okay, this is a, it will be just mu naught by, so small magnetic field will be equal to just dB cos theta or mu naught by 4 pi I dl by r squared. And r squared here, what will be the value of r squared? R squared will be nothing but, because this is a tangent in a 3D view, this is a tangent, so this forms a right angle triangle. So r squared will be equal to a squared plus d squared. So r squared I can just, from Pythagoras theorem, I can just replace by, from this triangle r squared is equal to a squared plus this squared, and this squared is nothing but d squared. So excuse me, so r squared will be equal to a squared plus d squared. And cos theta, so if this is theta, okay, if this is theta, then this will also be theta and this will be 90 minus theta. This simple trigonometry you can work it out, that if this is theta, because this angle plus this angle is 90 degree, and also because this angle plus this angle is equal to 90 degree, so this angle should be equal to theta, and because this is 90 degree, so this angle should be equal to 90 degree minus theta. So the value of cos theta here will be equal to, if this is 90 degree minus theta, then cos theta will be equal to sine of 90 minus theta, and sine of 90 minus theta is nothing but a. So let me work it out if you are getting confused. Cos theta will be equal to sine of 90 minus theta. So cos theta, if cos theta is sine of 90 minus theta, which is sine of this angle, and sine of this angle is equal to the opposite side, which is A divided by R. Okay. So, cos theta I can write it as A square root of R. R is nothing but square root of A squared plus D squared. So, small magnetic field dB will be equal to mu naught by 4 pi I, A will be there, divided by square. Now, A squared plus D squared into square root of A squared plus D squared is A squared plus D squared to the power 3 by 2, and there is a dl here. Okay. Again, it is a very simple integration. Just integrate this. If I will take all the constants out of this integration, radius is same of the circular loop. I am not changing the radius. I am also not changing the point where I am finding the distance. D is same. So, this will become B is equal to mu naught I by IA by 4 pi A squared plus D squared to the power 3 by 2 integration. All these constants are taken out of integration, find integral dl. Now, again same method, because dl is a small element in the circular loop, and if I add all the small element, if I integrate all the dl, I will get that L. Integration of dl is L, and the total length of a circular wire is nothing but the circumference of a circle, which is 2 pi a. So, integration of dl will just be L, which I can replace by if I will erase this dl and I will replace it by 2 pi a. Okay. Again 2 pi will get cancelled by 2, and my final answer will be B is equal to mu naught I A squared by 2 factor is here, 2 A squared plus D squared, A squared plus D squared to the power 3 by 2. Now, you see here the magnetic field. If I again apply my right hand thumb rule. Okay, let me draw a new circle just to make it more clear, and this is my axis of the circle, or in front of the circle I will make in this color, back of the circle I will make in some other color. Okay, and I have made let the current flow in an anti-clockwise direction, and if a current flows in an anti-clockwise direction, if I use my right hand thumb rule, which we just discussed a few minutes ago, the direction of magnetic field will be like this. Okay, so it is a straight line along the axis of the circle. Okay, now it is behaving as if it is a dipole. You remember, like in an electric dipole, if I have a plus sign and a minus sign, then along the axis the electric field is a straight line. Okay. Similarly, if I have a magnet, this is north pole, this is south pole. Okay, inside the magnet the magnetic field lines will be like from south to north. Correct. So here, and it will be a straight line. So this circular loop along that, like here along the axis the magnetic field is in a straight line. Similarly, along a circular loop along the axis the magnetic field is a straight line. So here the magnetic field is acting okay, the magnetic field or the circular wire is actually acting as if it is a dipole. Okay. So, here this is inside this, it is like, if it is an anti-clockwise direction, it is like here it is north, here it is south, and there is a straight line of force as if somebody has kept a bar magnet here. Okay, as if somebody has kept a bar magnet here with a north pole and a south pole here, and inside this magnetic field is going along the axis in a straight line from south to north. So, that is why a circular loop behaves as if it is a magnetic dipole, which can be also another way of describing this is, suppose I have D very larger than A. Suppose if D is very large than A, okay, then I can reduce this. I can neglect A, okay, I can neglect the term A here, because D is very large than A. So, A square plus D square, because D is very large than A, is almost equal to D squared. Addition of A square will make no difference. So, this will be equal to, if D is very greater than A, then mu naught I A squared by 2 D squared to the power 3 by 2, which will be D cubed, just neglecting the value of A here. Okay. Or I can write it as, I can further, why I am writing in this form is, which you will come to know shortly, but I can write it as 2 mu naught, this I can write it as 2 mu I pi A squared divided by 4 pi D cubed. Okay. What I just did, I multiplied numerator with 2 and denominator with 2. So, numerator have a 2 term here and denominator becomes 4. Okay. I also multiplied numerator with pi and denominator also with pi, numerator and denominator with pi. So, there is a term pi in numerator as well as denominator. Now, if you go back to electrostatic dipole chapter, then at the axis, the electric field due to an electric dipole at the axis is given by E is equal to 1 by 4 pi epsilon naught 2 p by D cubed. Okay. Okay. Now, just compare these two equations. Okay. They are very similar to each other. Okay. There is a 2 term here. Okay. There is a 2 term here, and there is a constant. In this case, the constant is 1 by 4 pi epsilon naught. Here the constant is mu naught by 4 pi. Okay. Here the constant is 1 by 4 pi epsilon naught. Here the constant is mu naught by 4 pi, and P can be replaced by I by P is equivalent to, or the dipole moment is equivalent to I into the area. Okay, current into area, and D cube are common. So, there are two ways of thinking that this circular loop acts as a dipole. One is if you compare the direction of magnetic field inside a bar magnet, you will find it similar. Also, you can also convince yourself that this acts as a dipole by comparing the equation of a dipole from electric dipoles and noticing that they are almost similar if I consider D is very greater than A. So, this is one important point to remember, that a circular carrying current loop, while loop, acts as a magnetic dipole because at the axis the magnetic field goes in a straight line. So I think this is what I have for you for this video. I will see you in the next video with some more discussion on magnetic field, namely the Ampere's law and some applications of Ampere's law. So see you in the next video.